Okay, so two events are independent if the occurrence of one event does not affect the occurrence of the other, okay? Please underline not, okay? They do not affect one another. They're completely independent. An example of independent events would be flipping a coin and doing what? What else would be independent of flipping a coin? Yes. What would be independent of flipping a coin? Come on, guys. Rolling a dice. Flipping a coin / rolling a dice. Okay? Two events are dependent events if the occurrence of one event does affect the occurrence of the other. So, do you see like how this little guy is picking out marbles from a jar of marbles, right? These would be, maybe if he picked one marble, would that affect the probability of him picking another marble? Yes, because first of all, the jar has one less marble, and second of all, let's say he picked a green one. Is he less likely to pick another green one? Yes, so those events depend on each other. Okay? Now, this is super important because when you're solving these equations, there's two different formulas, one for independent events and one for dependent events that you use to solve probability. Okay? So, all that we did yesterday, those were all what kind of events? Independent, okay? We're going to look at dependent events, and then we're going to compare their two equations, okay? Flipping a coin versus rolling a dice are two independent events, okay? Independent events would be flipping a coin and rolling a dice.
What's the flipping the coin one? You said that's independent.
Example 1, tell whether the events are independent or dependent. A box containing yellow and brown dog treats. You randomly choose one dog treat from the box and you do not replace it. Then you randomly choose another dog treat. Are these dependent or independent events? They're dependent. Why? Very good. Okay? You're not replacing them. So if you chose a yellow dog treat the first round, are you more likely or less likely to pick a brown dog treat the second round? You're more likely to pick brown because there's one less yellow. Do you see how they depend on each other? This is a dependent example, okay? Now, let's say you have a jar with red and blue marbles. You randomly choose a marble from the jar, and then you replace it. Then you randomly choose another marble. Independent or dependent? These are independent. Why? Very good. Okay? If you put the marble back, aren't you back at the original probability that you had from the beginning? So these events do not affect each other. Okay? The events are independent of one another. Okay? By putting the marble back, you've replaced the marble that you took the first time, so you're back at the original probability. You haven't changed event number 2, or event B. Questions so far? Okay. Conditional probability, okay? The probability that event B occurs, given that event A has occurred, is called the conditional probability of B given A, and is written probability of B equals probability of B given A, okay? This is what we're going to use for dependent events.
Is that a slash mark in between the B and A?
Correct, okay? Events. I'll write it down here. It's probability of B equals the probability of B with a line, almost like an absolute value sign, and then A. Okay? Yes?
So it's not a slash, it's just a line.
No, it's just a line, vertical line, okay? It's a vertical line, straight up and down. Yeah. That makes sense? It's not a slash. This is not being at an angle.
It's not a slash.
Okay? It's not like a fraction sign. All right? So what this is saying is, given A has already happened, what's the probability of B happening? Okay? Now, when two events are independent, take a look at independent events, okay? Do you see how we don't use the given portion? We don't use conditional probability. Why don't we use conditional probability when we're finding the probability of A and B happening? Why do you think we don't use conditional probability? Correct. They don't affect each other, right? They're independent, right? So does the probability of A happening affect the probability of B? No, okay? They're two independent events. Now, check it out. For dependent events, those absolutely affect each other. So the probability is different, okay? So the probability of A and B happening will be the probability of A happening multiplied by the probability of B given A, okay? This is going to be a different value than just your probability of B, okay? So what we saw yesterday was this. We would take two events, we would multiply their probabilities together to find the probability of this and this happening. Today, we are going to take a look at dependent events where one thing affects the other. Yes?
On the quiz, will there be, are we going to do a quiz on this before the end of the year?
You are.
Okay, so on the quiz, will there be an instance where we have to
So, check it out. Conditional probability, okay? So, do you guys agree? Let's just rewrite the original formula, which was probability of A and B equals probability of A times the probability of B given A. We can divide both sides by the probability of A and end up with this formula down here, okay? So the probability of B given A is going to be the probability of A and B divided by the probability of A. How we got this formula was all we did was we divided both sides by the probability of A, and we got to this formula. So if you remember this one, you'll be able to figure out the one below it. Xavier, you have a question? Yes. The line right here, ignore it. That's a typo, okay? It should not be there. Okay. Example 3. You spin the spinner shown, which is divided into 8 equal parts. Find the probability that you get red on your first spin and blue on your second spin. Guys, are these two independent or dependent events? They're independent. Does anyone know why they're independent?
Because you're not taking anything away.
Correct. If we rolled red, or if we spun red on the first go around, right? Would that affect spinning red, blue, or green on the second round? No, they're independent of each other. Do you guys see that? Okay, so how do we find the probability of rolling if A being red and B being blue? How do we find the probability of A and B? If they're independent, what's our formula?
Correction, Annalise Prieto, please report to student services. Annalise Prieto, report to student services.
Zoe?
Is it P, A, and B?
Very good.
Divided by P and A?
No, that's conditional, okay? I'm glad that you're using one of the formulas, but remember, these are independent events. Go back in your notes. What was the probability formula for probability of A and B for independent events? Carlos?
Probability of A times probability of B.
Very good. Probability of A times probability of B. They do not affect one another. You guys clear on that? Okay, what is the probability that we spin a red on the first spin? What's the probability of our A event? Carlos?
3 over 8,
It's 3 over 8. How did you get that?
because I counted the 3 red
Very good. There's 3 red spaces, and there's a total of 8. So our probability of A is 3 over 8. What is the probability of B, our blue event? No, it's 2 blue spaces over 8 in total. What? Remember, it's always over your total sample space. How many possible scenarios are there here? 8, right? Because there's 8 spaces you could land on. So the probability of B happening would be 2 over 8. So we plug those in. The probability of A and B happening, the probability of rolling red and blue on the second one would be 3 over 8 times 2 over 8. What does that give me? 6 over 64, okay? Now, before you multiply, try to simplify. Is there anything we could simplify here, guys? Carlos?
3 over 32.
How'd you get that?
Dividing by 2.
Good. Cancel out the 2, make this a 1, make this a 4, then multiply across. You're going to get 3 over 32. Guys, we have to stop here. Dependent events. Mariana?
Because you had one, but then like they ate it, so you have to pick another one. So you have to get more like for that.
Correct. Dependent means that event A affects event B. Figure out how they affect each other, because your probability of picking a green grape the second time will not be the same as the probability of picking the green grape the first time. See if you can figure it out. Go. Let's go over this one, okay? So we have 2 events, event A and event B, okay? Since they're dependent, check out which equation we're going to use. We're going to use the probability that event A and B happen is equal to the probability of event A times what? The probability of B given A happened. Remember, this is the formula that we use for dependent events. If they were independent, right, and they did not affect each other, it would just be the probability of A times the probability of B. But do you guys agree, since they do affect each other, we have to use the probability of B given that A already happened? Yeah. Okay? That's what that line means, and that's what the A means after the B. Do we understand that? Okay. Now, the probability of A is easy. It's just like a normal probability event. What is the probability that the first grape that we pick is green? Who got that? Xavier, what'd you get?
36 over 50 or 18 over 25.
Very good. 36 over 50. Okay? Now, how did you get 36 over 50?
Because there's 36 green grapes and 50 yellow grapes.
Very good. There's 36 green over 50 in total. Okay? There's 36 green over 50 in total. So our probability of A happening is 36 over 50. Now Xavier simplified it. He divided both the numerator and the denominator by 2. So he got 18 over 25, right? Very good. Okay? Now, the probability of B given A, since these are dependent events, this should not be the same as the probability of A. Christian, what do you think it is? Oh, it's 11. Do you know what this is?
What?
The probability of B given A. Okay. Carlos, what do you think it is?
Isn't it 35 over 49?
It's 35 over 49. Why is it 35 over 49, Carlos?
Because you took one away, so you have to take one away from the entire thing. Not
Very good.
numerator and denominator.
Excellent. Guys, if they're dependent events, you have to assume event A happened. Event A says that the first grape was green, right? Assume we picked a green grape. How many total grapes do we have now in the second time we reach our hand in? You have 49 to pick from. So our denominator went down by how much? 1. But our green grapes also went down by 1. Do you see that? Now, how many purple grapes do we still have in the bag to choose from?
14.
14. That one doesn't change because we're assuming that the first grape that we picked was green. Do you guys understand that? So in that second probability, if they're dependent events, assume the first one happened, right? So we have 18 over 25, and then we have 35 over 49. So the probability of A and B happening is going to be the probability of A, which is 18 over 25, times the probability of B given A, which was 35 over 49.
Wait, can't you make that to 5 over 7?
You can because they're both divisible by 7. Very good, okay? So let's change that to 5 over 7, because these are both divisible by 7, so it'd be 5 over 7, 5 over 7, okay? So the probability of A and B. Guys, how do we multiply fractions? No. You multiply straight across, okay? Do not, guys, this is very, very important, okay? I see this a lot. Please do not cross multiply, okay? If you cross multiply it, leave it on your page and cross it out and write a note to yourself. That is not what I do. You multiply straight across, so we're going to multiply the 18 and the 5, and we're going to get what?
You can simplify, right?
18 times 5 gives me 90 over 25 times 7.
Can't you simplify that?
Hold on.
Okay.
So we're going to get 175, okay? Now, you can leave, it just said find the probability, right? If you leave your answer as a fraction, it must be a simplified fraction, okay? That means you need to simplify this further. What are 90 and 175 both divisible by? 5, okay? So 90 divided by 5 is 18, and 175 divided by 5 is 35. Can we simplify that any further? No. So this would be our final simplified answer. Now, if you're like, I hate fractions, this just said find the probability. You can also leave it in terms of a decimal or in terms of a percentage, okay? So let's go ahead and calculate it. Let's do 90 divided by 175. I got 51.4 or 0.514. Yes? So it's 0.514. That would be an acceptable answer. And then you could also change it to a percentage as 51.4%. Okay, now, what if this question said that we replace the green grape before we choose the second grape? How would that change this problem? If this question said, after we pick the first grape, we replace that grape, and then we choose the second grape. It makes it independent. So what would be my two percentages, or my two probabilities? It would be 36 over 50, and then what? 36 over 50. Because we have the same likelihood of picking the green grape, right? Both times. So it would be probability of A times probability of B. Do you guys see the difference there? So with replacement, your probabilities are going to stay the same, right? It's a fixed probability. But when you have dependent events where you don't replace it, that you have to assume that the first event happened. So something's going to change in your probability. Questions? Yes.
When it's independent, then it means, so then you don't assume that the first one happened.
Correct. Okay? They're two independent. They don't affect each other. Okay? So that would be something where you do replace it. Because if you pick a grape, right, and then you put it back, has anything changed about the number of grapes? No. Okay? Everything's still the same. Very good. All right. Let's move on. So, example 5. Guys, we covered everything that we need to know. Now we're just doing examples. Okay? So in example 5, it says, tell whether the situation describes independent or dependent events, and then answer the question. Okay? Number 1, a drawer contains 12 white socks and 8 black socks. You randomly choose one sock. You do not replace it. Then you randomly choose another sock. What is the probability that both socks chosen are white? Is this dependent or independent? Christina, what? Independent. We are not replacing it.
So it would be dependent.
So they do depend on each other, okay? Okay, think about it like this. Do not replace starts with a D, right? that's dependent. Make sense? Do not replace, dependent. If you replace it, it's independent. What?
Is it always going to be after?
Not necessarily.
Maybe just gotta like for independent,
Whether
it's gonna
it's
say that they replace it.
So it will not always say do not replace. It could say that they replace it. If it says that they replace it, then it's independent. Okay? All right. So what is event A? What are we looking to happen the first time? What are we looking to happen the first time? Because there's two things that are happening here. What is event A? What's the first thing that we're choosing? Or the first event that we want to happen? What? Pick one of the socks. But specifically, what do we want to pick? Choose one white sock. So in event A, we've chosen one white sock. Okay? And what would event B be? It would be choose another white sock. Okay, so we agree that these are dependent events, right? So event A is just normal. What is the probability that I pick a white sock? Mariana? 12 over 20. How did you get that?
Because 12 is the number of white socks and 12 plus 8 is the total.
Very good. The total is 20, and we're going to pick out of 12 white socks, we're going to pick one of those out of 20 in total. Does this simplify?
Yeah.
What is 12 and 20 both divisible by? 2. Actually, there's a bigger number, by 4. Okay, so this should be 3 over 5. So the probability of A happening is 3 over 5. The probability of B, given A. The probability of B, given A, is what? 11 over 19. How did you get that? Very good. Assume event A happened. If we picked one white sock, how many white socks are left in our pile? 11. Do you guys see that? Our white socks went down by 1. What also went down by 1?
Our total.
The total number. Do you guys see that? So they both decrease. Okay? So we have 11 out of 19 socks now to pick. Does that fraction simplify? No. So the probability of picking A and B is going to be equal to what? Christian?
33 over 95.
Very good. We take 3 over 5 and we multiply it by 11 over 19. And you said it's 33 over what?
95.
95. We can leave it like this because this is a simplified fraction. How else could we write it? Remember, it just says what is the probability. It doesn't say we have to list it as a percentage or anything. Zoe?
A decimal?
Did you plug it into your calculator?
Yeah.
What'd you get?
0.347.
Very good. 0.347. And then lastly, we could write it as a percentage. What is this as a percentage?
About like 35%.
About 35. I would leave it as 34.7%. Okay. Any of these three answers are acceptable. Okay. But the first one as a fraction needs to be simplified. So if you can simplify your fraction, simplify it. Okay. If you're not comfortable with fractions, just change it into a decimal or a percentage. But all of these three mean the same thing. And no. Okay. Very good point. Please, 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 as a decimal form, round to your third digit. Okay. Round to your third digit, which is the thousandths place, okay? Because we want it, if we write it as a percentage, we want it rounded to the tens place as a percentage. Talia? Yes. Okay. Okay. Example 2. Suppose you flip a coin twice. What is the probability that you get tails on the first flip and tails on the second flip? Okay. Now, the first thing we need to identify is this independent or dependent events. Independent or dependent events. These are independent. Does anyone know why they're independent?
You don't have to replace anything.
You don't have to replace anything. Does flipping a coin one time affect what you flip the next time? No, so they have nothing to do with each other. Do you guys agree? So flipping the coin is completely independent, okay? So we're going to use a different formula. The probability of A and B is just equal to the probability of A times the probability of B. Do you guys see how the formula changed? This is no longer assuming that A happened, right? Because they don't affect each other, okay? So, event A, what do we want to happen in the first event?
Flip tails.
Event A is we flip tails, right? And then event B, what do we want to happen?
Tails.
You flip tails again.
Why do you say tails in that?
What?
Why do you say tails?
Because what does it say at the very end? It says, what is the probability that you get tails on the first and tails on the second? Okay? So we're using our events to match whatever we want to find. All right, guys. So what would the probability of event A, what would the probability of flipping tails on the first flip be?
1/2.
1/2. Because it's tails is one of the two outcomes, right? And there's two possible outcomes. You have a 50-50 chance of flipping heads, and you have a 50-50 chance of flipping tails. So 1/2. What is the probability of the second of flipping tails the second time? 1/2. Okay? They're independent events, so they don't affect each other, right? Like if you pick up the coin the second time, flipping tails the first time does not affect what you flip the second time. It's still 1/2. So we take those values and we multiply them. So we're going to get the probability of A and B is equal to 1/2 times 1/2, which gives me 1/4. As a decimal, this is 0.25 or 25%.
Those 4 outcomes.
Absolutely. So do you guys remember in the first lesson where I had you write like heads, 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 tails, tails, heads, and tails, tails, right? And I had you list them all out. And our one possibility was out of 4 total. Do you see how we got 1/4 as well? So I'm showing you an easier way or a faster way to do it, okay? But you have to identify whether they're independent or dependent events. But Sophia, absolutely, you can use the first method that we did.
So only
Yeah.
for independent events, Matt?
For this one,
Only for independent events could you use this?
correct. Yes.
When I asked you when we were doing that, this is the only way, you said yes, so we can use it.
When we covered 9.1, this was the only way that we knew how to do it.
Oh.
Okay, now I'm showing you another way. Does that make sense? 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and B, the probability that a hurricane is in the northern hemisphere, okay? All right, so how we read this table, okay? This table is called a two-way table, okay? It lists the northern hemisphere and the southern hemisphere. And then it tells us, okay, in the northern hemisphere, we have depressions, storms, and hurricanes. And we have depressions, storms, and hurricanes in the southern hemisphere. So what does the number 199 mean? Stephanie? Very good. It would mean the number of tropical depressions in the northern hemisphere. Do you guys see that? And what would the number 18 represent?
The number in the southern.
The number of tropical depressions in the southern hemisphere. So if I were to ask you, what is the total number of depressions, tropical depressions, how many would you guys say there are? 217. How'd you get that, Carlos? You added them together, okay? So there's 217 total tropical depressions. Do you guys see that? So any column or any row will be the total number of like tropical depressions, tropical storms, tropical hurricanes. Now, what if I said, what is the total number of storms, whether it's depressions, tropical storms, or hurricanes in the northern hemisphere? What's the total number?
590.
Nope.
Oh,
Like
not
of
tropical.
In the northern hemisphere. What are the total number of storms in total, doesn't matter which kind, in the northern hemisphere?
1,100.
Wait, like
1,142. How'd you get that, Janellis?
I added all of the northern together.
You added all of the northern together. Do you guys see that? Okay, so how this table works is it shows a total of 6 different numbers, right? Each of them represents whatever 2 column or rows they link up to. So the 199 is the number of northern hemispheric tropical depressions. And then if we added all the numbers in the northern hemisphere, we would get the total number of storms in that hemisphere. Make sense? What's the total number of storms in the southern hemisphere, guys?
433.
433? How'd you get that?
Add them all together.
Very good. Okay. Are we cool on how to read this? Okay. So if it asks us in A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane. Okay? What's the probability that a storm in the northern hemisphere is a hurricane? Xavier?
545 over 1,142.
How did you get that?
Because there's 545 hurricanes and 1142 total storms.
Very good. So what we're looking for is the probability that a cyclone, it's already in the northern hemisphere, is a hurricane. Okay? And the probability that a cyclone in the northern hemisphere is a hurricane is the number of hurricanes in the northern hemisphere divided by the total number of storms in that hemisphere. Okay? So the 1,142 came from here, and the 545 came from the number of hurricanes in that hemisphere. Okay? If we were to simplify that, 545 divided by 1,142 for 0.477, which is 47.7%. Okay, B is asking the probability that a hurricane is in the northern hemisphere.
So then you just do the same thing with the 433.
So the probability that a hurricane is in northern hemisphere. This one's a little bit different. Okay? So remember, the probability that a hurricane is in the northern hemisphere, we have to find the total number of what? Hurricanes. Very good. What is the total number of hurricanes, guys?
760.
760. How'd you get that?
I added the 545 and 250.
Good. 545 plus the 215 is 760. That's the total number of hurricanes. So the total hurricanes is our denominator. What's our numerator?
1,575.
Nope.
It's 545.
Why?
Because it's northern.
Northern hemisphere hurricanes. Okay? So it would be 545 over 760. This fraction can simplify. They're both divisible by 5. Divided by 5. 109. And 760 divided by 5. 152. Let's just divide them. 71.7 or 0.717, which is 71.7%. Remember, any of these answers are acceptable. Questions? Okay, one more and then we're done. You randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is not a heart and the second is a heart? A, if you replace the first card before selecting the second, and B, if you do not replace the first card, okay? So, Let's do A first. If we replace the first card, independent or dependent events? Independent. Why?
Because you replaced the first card.
Very good. So if we replace the first card, is that going to affect what the second card will be? No. Okay. So if they're independent, what's my event A? What do I want to happen first?
Not getting the heart.
Not a heart. And what was event B?
Getting the heart.
It was getting a heart. Hold on. Let me finish this problem. So, what would be the probability of event A? Remember, probability of event A isn't affected because it's the first event to happen. Xavier?
You take 1 and 39 over 52 because there's 52 divided by 4 because there's 4 different classes of cards.
Mm-hmm.
That's 13. 52 minus 13 is 39. And then that's 20 cards left.
Absolutely. Okay. So, yes. 52, we divided it by 4. Okay. Xavier divided by 4 because there's 13 hearts, right? There's 13 spades. I'm not even going to try to draw the spade symbol. There's 13 clubs. And there's 13 diamonds. Do you guys agree? In a deck of cards? Okay, if you don't know which suits are in cards, please make sure that you know that for the...
Like you have to know the spades and the blue.
Correct. Okay? There's 13 hearts, there's 13 spades, there's 13 clubs, and then there's 13 diamonds. Okay? So, we are finding the probability of not getting a heart. And not getting a heart would be 13, 13, and 13. You could either pick up a club, a diamond, or a spade. 13 times 3 is 39. So we have 39 to choose from out of 52. Right? Or 52 minus 13 gives me 39 as well. Okay? Then we have to calculate the probability of B. Now, we don't care what happened in probability of A because we're replacing that card. So it doesn't affect probability of B. You guys cool with that? Because they're independent events. So what would be the probability of getting a heart on the second draw? 52 is still the denominator. But how many hearts do we have to pick from? 13. So if we're finding the probability of A and B, what do I do with my two probabilities? You multiply them. So we're going to do, this is going to be probability of A times probability of B. Because remember, these are independent, right? The first time around. Because we're replacing them. So the probability of A and B is going to be 39 over 52 times 13 over 52. You multiply them. 39 times 13, 507 over 52 times 52, 2,704. Just divide those. So 507 divided by 2,704, 0.188, which is 18.8%. So there's an 18.8% that this happens with replacement. Let's see what happens without replacement, okay? If we are not replacing them, are they dependent or independent events? If we're not replacing it.
No, it is dependent.
They're dependent. Do they depend on one another? Okay. So the probability of A is not going to change, right? Because that's our first event. What would the probability of A be, Christian? 39 over 52. Now, Christian, what would the probability of B, given A already happened, what would that now be? 13 over 51. Take a look at this, guys. Why did the 13 not change? What did we pick the first time? We didn't get a heart. So is that going to change the number of hearts in the deck? No, there's still going to be 13. But what did change? The total number of cards. Because now we're down one card, right? We have one less card to pick from, but we know that the card that we picked the first time was not a heart. So we still have 13 hearts to pick from, but it's out of 51. Make sense? Okay, so the probability of A and B, given that these are dependent events, will be the probability of A times the probability of B, given A already happened. So the probability of A and B equals 39 over 52 times 13 over 51. 39 times 13 gives me 507 over 52 times 51, 2,652. So 507 divided by 2652, 0.191, which is 19.1%. So which one is more likely to happen? If I replace them or if I don't replace them? If I do replace them, okay? Do you see how the 19 is bigger than the 18? So there's a bigger chance that I pick out a heart if I don't replace them, okay? If I don't replace them, I think I said that wrong. If you don't replace them, okay, you have a greater chance of picking both of these, okay? The first percentage does not change, right? Picking a heart the first time around, or not picking a heart the first time around, that's going to be the same percentage. But your second event, okay, that changed. It was 13 over 52 the first time we did it because we did replace, and it was 13 over 51 if we did not replace it.